So we talked about matter, we talked about energy, and now I should mention that they can interact with one another. And so we use these terms system and surroundings, and we'll use them throughout the entire year. The system is like what you're trying to study, and the surroundings are just that, whatever's surrounding it. And so, for example, I could have a reaction happening in the beaker, and the system would be the chemicals that are inside the beaker. What compounds are in the beaker, what elements are in the beaker. That would be part of the system, what I'm studying. The surroundings might be the glass beaker itself, the surrounding air. And so often when we think about an energy change, we think about the energy change in like terms of what direction is the energy flowing. Is it flowing from the system to the surroundings? In that case, we call the change exothermic. That's where energy flows from the system to the surroundings. Whoa, you stinker. There we go. From the system to the surroundings. And so if I have a reaction happening in a beaker, and that reaction is exothermic, I'm thinking of it like this. So here's my beaker, and here's my chemicals or whatever's in the beaker. And if it's giving off energy, that energy is going from my chemicals, the system, into the surroundings. And the surroundings could be the glass beaker. So the beaker's going to feel hot to the touch. And it could be the air. Like sometimes maybe we would put our hand above the beaker and be like, ooh, it's getting warm. But often when we feel the surroundings, it's the surrounding beaker or air, it feels warm to the touch when there's an exothermic change occurring. Now the opposite is true of an endothermic change. So if I have an endothermic is where energy flows from the surroundings into the system. So if I think about like my beaker example, I'll make a blue beaker again. Okay, so here's my beaker, move it. And I've got like some chemicals in the beaker and there's a reaction occurring, but it's an endothermic change. So endothermic would mean that the system, these chemicals, are absorbing energy from the surroundings. The surroundings then are going to feel cool to the touch. If I feel the beaker lacks energy now. Some of the energy from the glass particles in the beaker got sucked into my system. That energy got sucked into the chemicals that were inside of the beaker. So I feel that lack of energy. And so here there's an example of gallium. Gallium's kind of an interesting metal. Some would even refer to it as a metalloid. And most metals have pretty high melting points, but gallium does not. Gallium has a pretty low melting point. It melts at, I think, 28 degrees Celsius or about 85 degrees Fahrenheit. And so just the heat from your body is enough to melt gallium, which is not the case of most metals. I mean, like I could hold pennies in my hand and I can't make them melt. So it says that solid gallium has a definite shape, a definite volume. And so it might look kind of like this picture of a solid where the atoms are packed real tight, not a lot of energy. Gallium atoms in solid phase have less kinetic energy than liquid phase. And so then they're trying to show maybe a picture of liquid gallium where the particles have a little more space between them. They're trying to show that they have a little more energy, they can move around a little more. Liquid gallium flows into different shapes. The volume would stay the same, and whether it's solid or liquid, you've got the same amount of gallium atoms. We're just changing their shape so they can take on the shape of different containers, especially now that the particles have a little more room between them that they can move and flow. A little bit more kinetic energy. And so in this example, if you put gallium in your hand and it starts to melt, and melting is an endothermic process. And it takes energy to go from solid to liquid. I had to add energy. In the liquid phase, the particles have more energy. There's more movement. Well, where's that energy coming from? Well, it comes from the surroundings. So it's going to come from the surrounding air and, most importantly, your body heat. And so we have something that might look kind of like this. Let's pick another color. So the energy is going from the hand into the gallium. And so there's an exchange in energy. For the gallium to melt, it requires energy. It gets that energy from its surroundings. The gallium would be considered the system. So when matter and energy interact with each other, there's always some kind of a change. And often they're really cool. So with that then, question 7, a cross-cutting concept on systems and system models. Liquid gallium changes to a gas at over 2,000 degrees Celsius. I cannot do that. I'll post a little video where I do have solid gallium and I can melt it, but I don't have any means of like vaporizing the gallium, nor would I really want to. I cannot get that gallium to 2,000 degrees. So it'll just stay as a solid and liquid, which is still fun. Describe how a model of gaseous gallium would compare to the model of liquid gallium shown in the picture. And so hopefully you drew some kind of a picture where now maybe we would say that the gaseous gallium would just have particles that are farther apart from each other. Maybe something like this. And maybe you tried to show in some way that the particles have more energy, that they have more movement, and so maybe you kind of like do some little arrows where the particles can bounce all over the place, and they don't have to like take a particular shape or form. They can bounce wherever they want to. They can fill the entire container, whatever that container might be. Question 8, a science and engineering practice. What do scientists do? They evaluate models. In this experience, you studied the particle nature of matter. Matter is made of particles. And learned that each atom of any element is identical to every other atom of that particular element. Does your model of color generation... Okay, so we were looking at like the colors generated by fireworks early on. Does your model of color generation make use of the particle nature of matter? And so this is kind of a what do you think kind of question. Not that there's a right or wrong answer. That do you think maybe there's something different in different fireworks that's causing these different colors? And I mean, it's all related to like light energy, right? And maybe you start thinking about like the electromagnetic spectrum, the Roy G. Biv. Like if I see like reds and oranges, that's a low energy color. So does that have to do with the type of particles or the type of elements or compounds that are being used? And like your blues and violets are higher energy colors. Is it an endothermic process, exothermic process when I see these different colors of light in the sky? How can you use the definition of an element to improve your model? And so, again, this is just whatever you think and whatever you made for an initial model. But now can you maybe think that, I don't know, maybe there's different elements or something different about the compounds or the elements in the compounds that are causing these different observations?